What's up, guys? It's Mr. Bringle, and today we're going to be talking about energy bar charts, sometimes referred to as LOL charts, and evaluating energy transformation and conservation with these types of energy charts. Previously, we've worked on energy pie charts. This is very, very similar, but just showing it in a different way. So let's go ahead and jump right in here. So it says for each situation below, list the objects in the system within the circle and always include the Earth's gravitational field in your system. So the system is basically us defining objects and things that we are going to study for this particular problem. And we're setting a boundary, and we can evaluate what's going on within the system, and then was there some sort of additive to the system from outside, or does anything leave the system? And this will be easier to understand as we do some examples. So just hang with me as we go through this here. So let's go ahead and continue to read through the instructions, and then we'll go back and we'll do all these things. So on the physical diagram, we're going to indicate our choice of zero height. We'll just do that at the base level for this problem here. And then we are going to sketch an energy bar graph for position A over here, which goes into this bar chart here. Position A goes into this bar chart, position B goes into this bar chart, okay? And then we will go ahead and write out an equation that explains the energy transfer going on here. So problem 1A, in the situation shown below, a spring launches a roller coaster cart from rest on a frictionless track into a vertical loop. Assume the system consists of the cart, the earth, the track, and the spring. So let's go ahead and write the things that are part of our system here. So we have cart, we have the earth, we have the track, and we have the spring. So to be clear here, the reason why the earth is part of our system, which will be a part of every system, is so that we can include gravitational potential energy, okay? So that is not necessarily saying that that's the ground, okay? So there might be a problem where an object is on some surface and the surface might not be part of the system, okay? So in this case, the surface is the track. So don't ever assume that the earth is the ground. If like a car is rolling on the street, you would put the earth in the system, and then we would make a decision on whether the road is part of the system or not. Okay, so now from this point, we go ahead and we look at position A here, and what I am noticing at position A is that the spring is loaded up and the cart is sitting in front of it, right? So the cart is essentially an extension of the spring here. The spring is storing elastic energy at this point. So there's no kinetic energy because the object is not moving, and there's no gravitational potential energy because the object is at a height of 0 meters. I'll put this right here, height equals 0 meters right there. So what we're going to do is we're going to go ahead and make a bar chart that consists entirely of elastic energy on this first side here, and we're going to go with like bars of energy, right? So this would be 1, 2, 3, 4, 5 bars of energy. Now we know that energy can't be created or destroyed; it can only be transferred from one form to another. So we are going to need to make sure that we have exactly 5 bars of energy on the final side here too. So let's take a look at that. At position B, we see that the cart has gone up the loop and is in the middle of moving here. So it's got these whoosh things going off of it. It's still moving, so there's going to be kinetic energy, and it is at some non-zero height. So we know there's going to be gravitational potential energy as well. At this point, the spring is no longer compressed, so the elastic energy has been released. And in fact, that happens the moment after it launches the cart, right? Once that spring is no longer compressed, it's no longer storing elastic energy. And then thermal energy over here would be generated from friction, but please note that it told us it was a frictionless track. So we're going to get rid of elastic and thermal, and instead we're going to do some combination here of kinetic and gravitational. Now, it's arbitrary, right? We don't know exactly how much kinetic or exactly how much gravitational, but we just want to make sure that they add up to 5. So we could do something like, 2 kinetic, and that means we would have to do 3 gravitational, right? If you did it the other way around, that's okay. We just all want it to be relative to our example, and make sure that when we do like 1A and 1B and 1C, it's all relative to each other. And again, this will make more sense as we kind of go through that. But our equation here, we're just going to list the type of energy at position A, elastic energy, and we're going to set that equal to the energy on the final side, which would be kinetic energy plus gravitational potential energy. Okay, and then remember that each of these things has an equation. So elastic energy is 1/2 kx squared, kinetic energy 1/2 mv squared, and gravitational potential energy mgh. So we could sub all those things in and solve for some variable with a math problem. We won't do that today, but we will in the future. So there is problem 1A. We're now going to move on to problem 1B, which is the same problem. It says repeat problem 1A for a frictionless system that includes the cart, the earth, and the track, but not the spring. So now the spring is outside of our system, which is going to change some things. So I'm going to go ahead and go back to my system here. It said the cart, the earth, the track, but not the spring. So what we're going to do is we're going to draw the spring on the outside of the system like this, okay? Now, what we will do is evaluate this without the elastic energy as part of the system. Now, the spring still stores elastic energy, right? But we have defined our system to be such that the spring is not part of it. We will therefore not include the elastic energy in the bar chart. Instead, what we're going to show is that the spring is adding energy to the system here, okay? And the way that we'll do this is we'll put basically like hash marks on our arrow to indicate more or less the bars of energy, right? So this is going to be 1, 2, 3, 4, and I'm going to add a fifth one down here. So there's 5 bars of energy. In fact, what I would prefer is just go ahead and write the number next to it so that it's very, very clear as to what we're doing there. I'm going to move this up here so that we can see the rest of this. Now, this takes care of the elastic energy that we accounted for on the first problem. So we've basically taken the elastic energy that was in the bar chart, and now we're showing it entering the system from the outside, okay? And again, the definition of our system is just a way for us to look at the problem. We're now looking at the problem from a different perspective, essentially. Okay, so the spring adds energy to the system, and we would say that the spring does work to the system. That's what we would, basically it does work to the cart. Okay, so we'll get to that here in a minute. Now, the final side of our problem should be no different, right? Because the cart is still moving at the top, and it still has gravitational potential energy because it's at the same height. So we've got 2 bars of kinetic, 3 bars of gravitational, and I do apologize. I want you to list the number above these things. I did not do that on number 1, so that is my bad. But go ahead and write those numbers above it, and make sure they always add up to whatever was the energy input was, right? So whether it's on position A bar chart or whether it is coming from outside the system, this number has to match these here. Okay, now we go ahead and we write our equation. Now this time we're not going to say elastic energy because that was not part of the system. Instead, we are going to say work. So the spring does work on the cart, and remember, work is equal to change in energy. Well, the change in energy of the cart is the final side here. So the work, in this case, done by the spring, is going to be equal to the kinetic energy gain of the cart plus the gravitational potential energy gain of the cart. Okay, so again, essentially the same problem, different perspective, either elastic energy being transferred to kinetic and gravitational, or we would say, if the spring is not part of the system, that work was done by the spring on the cart, and the cart then gains energy as a result. Okay, let's go ahead and move on to problem 1C. It says use the same system as problem 1A, so that's going to be cart, track, earth, and spring. So the spring's back in the system, but assume that there is friction between the cart and the track. Okay, so now that the spring's back in the system, we go right back to identifying the energy stored in the spring, which is elastic energy on the initial side. On the final side, we're still going to have kinetic energy. We're still going to have gravitational potential energy. There's no elastic, but the thing that we need to include here now is going to be thermal energy due to friction. So heat will be generated. So basically, we have to have at least 1 bar of thermal energy, which means that something has to be subtracted from something else. You got to be careful here, though, because there is one of the two things that we need to subtract from, and we should not subtract from the other. Before, we had 2 bars of kinetic and 3 bars of gravitational. If I leave it like this, we have an imbalance. We have 5 bars of energy on the initial side, and we would have 6 on the final side. So, do we take away from kinetic or gravitational, or both? In this case, the object at position B is at the same height that it was in problem A. So we really shouldn't subtract from gravitational potential energy. This should stay as 3 bars, just like it was in problem 1A. Instead, what we want to do is we want to go ahead and subtract from the kinetic energy, because the cart is going to slow down when it experiences friction. So at this point, point B, it's in the same location vertically, but it's moving a little bit slower. So we decrease that kinetic energy to show that, and now we can see that it adds up to 5. In this case, our equation, energy conservation equation, the elastic energy stored in the spring is converted into kinetic energy from the cart moving plus gravitational potential energy of the height of the cart, and then thermal energy that was generated from friction. Okay. Let's go ahead and move on to our last example here, which will be problem 1D. And in this scenario, it says, assume, or this situation is the same as problem 1A, except the final position of the cart is lower on the track. So this one actually needs to be redrawn. We're going to get rid of position B right here, and we're just going to redraw the cart over here as if it had gone a little bit further around the track. So we'll call this position B. So now it's at a lower height, okay? Going back to our system, we still have the cart, the track, the earth, and the spring. So same as problem 1A. And then it says make sure our bars are scaled consistently between problems 1A and 1D. So we just need to make sure that we are including a different amount of gravitational potential energy relative to what we had in problem 1A. Okay, so on the initial side here, once again, still elastic energy that's stored in the spring. 5 bars of energy there. On the final side, we have to consider, again, there's no elastic energy because the spring is decompressed, and we're not including friction here because problem 1A did not have friction. What we originally had in problem 1A was 2 kinetic, 3 gravitational. But now the cart is lower. So if we subtract a bar of gravitational potential energy to show that it is at a lower height, we now only have 4 bars of energy. So we must increase the kinetic energy by 1 bar, because if it has gone down the ramp here, the loop, it's going to be moving faster than it was up here at the top, right? Because gravity's acting on it, it's accelerating as it goes down. So now we've just flipped them, and there's more kinetic than there is gravitational. Our equation ends up being the same as 1A, though. The elastic energy from the spring is then converted into kinetic energy plus gravitational. It's just that those would be different values, okay? So this will conclude our notes over energy bar charts, also known as LOL charts, going over energy transformation and conservation. So your next objective will be to take a stab at problem number 2 and try that one on your own. Thanks for sticking with me, and I hope you learned something.